So, is this one? Mic is here?
Yes.
Okay,
Yes,
Sarah, can you hear me?
Okay, good morning. Today we come back to another session of private activities, and the presentation today is about seismic performance of steel frames accounting for the behavior of the three-dimensional joints, and the presentation will be made by Melaku during 20 minutes.
Thank you. Thank you all for here to attend this presentation. As you said, I don't know if I'm done in time or not. Most of you here know my name, but for those listening to us on YouTube, I'll introduce myself. My name is Melaku, and today I'll be presenting to you the research work that we have conducted in the scope of my PhD thesis, which is supervised by Professor Luís Simões da Silva and Professor Carlos Rivera. The title goes as Seismic Performance of Steel Frames Accounting for the Behavior of Three-Dimensional Joints. My presentation has the following layout. I'll first be giving some introduction. This will be followed by the basic work done in two-dimensional frames and a literature review that was done to provide the research questions will be presented later. The pretest numerical simulations will be shortly presented afterwards, and then I'll be presenting the results of the completed experimental times and show you what is being done currently in the last few slides. So, the scope and objective of this work is mainly, the end goal is to study the major and minor joint interactions in three-dimensional joints where beam comes and frames into a column from both the major axis and the minor axis direction, and propose an appropriate modeling technique for structural analysis and assess the joints model's effects in design and also seismic performance. To do this, experimental tests will be carried out, a modeling tool will be developed, and then analysis and design routines will be developed, and the performance of the frames will be assessed using nonlinear analysis. The scope of this work is, for now, applicable to the type of joint topologies we studied, but probably scalable, and this is to be determined. This is the research structure and the tasks. The ones in red are completed tasks. The ongoing ones are in purple or pink, and the white ones are the ones that are to be yet completed. So it starts with task 1, where we work on 2D and then the literature review on three-dimensional joints. Task 2 is the numerical modeling part. Task 3 is the experimental part. Task 4 is the analytical mechanical development part. Task 5 is the nonlinear performance assessment. Task 6 is writing the thesis itself. To give an overall idea for people who are here who are not working in joints, in the area of joints, the joint behavior can be predicted through several ways, using analytical, empirical, experimental, mechanical, numerical, and nowadays informational models. And the joint can be represented in structural analysis using different ways or different methods of different degrees of accuracy, such as a linear one, bilinear model, multilinear model, or a complete nonlinear model. Apart from the behavior, the way how we include the joint in our model is also important. The most common is this one, where we use a linear center line model, where the nodes dimension is completely disregarded, and also the joint's behavior is completely taken as fixed or continuous. And then you have a bit more refined option, where you still have a center line model for the beams and the columns, bar elements, and at the ends, strings could be put to represent the behavior of the joint. Another, even more refined model would be the scissors model, which considers the dimension of the wet panel zone, but only considering it to be rigid, and is expressed by a string here that defines the rotation between these two vertical and horizontal elements. A much better and refined model would be the Cravinckler-Gupta model, which incorporates the node dimension, the wet panel zone, its deformation, and the behavior of the connection on either side. The kinematics of this and this model are different, as you can see here, with a better approximation of reality given by the Cravinckler model. So, with this, in 2018, I was involved in a project called Equal Joints, and this is a project for pre-qualification of joints in European code. It's a pre-code project, and the University of Coimbra had a task to study this joint, where a stiffened, extended plate and plate joint. From here, what we studied was dual concentrically braced frames, as you would know. It's a composition of moment-resisting frame and concentrically braced frames, where not the total load goes to the braces, but to about 25% of the lateral forces is to be taken by the moment-resisting frame. However, in terms of seeing the effects in the design phase, the influence of the moment-resisting frame was truly, really insignificant, so not much was seen there. So the idea was, how about we test it for moment-resisting frames alone? And we did that. From doing that, we were able to notice that the designs that we came up with would pretty much always be oversized to fulfill the stability criteria given by the code, such that the effect of the joint would be overshadowed by the overstrains to affect the design. Of course, the performance is completely affected, but in terms of affecting the design, it was not showing much. But the scenario at that point was that we had the second generation of the Eurocode was underway, it still is underway, and the version 2020-21 was already available. And we could see that there were some significant changes made in this version. So the aim was, okay, so now let's see, perhaps this oversizing into the stability criteria, if it is resolved by this revised code, let's see if the joints would have significant effect at the design level, and let's see if the performance would be any different. So, to quantify that, we used a method where we modeled the joints using simplified models and also the refined model that I showed you earlier on, and assessed and designed and then assessed the performance using nonlinear analysis. So, the changes in the revised Eurocode 8 of that time are shown here. The main ones are that the definitions of the ductility classes were changed. So the ductility class medium and high, the naming was changed, and also was their definition. So the behavior factor given for ductility class 2 now is 3.5 for still moment resisting frames. And the behavior factor now is given as a product of three members, three individual behavior factors representing ductility, redundancy, and all other sources. The major other change here is that the formulation for the interstory drift theta was changed The previous code, the current code, sorry, because it's still under revision, so the current code is still valid. So theta always disregarded the behavior factor. So it was tougher for designers to go for lower sections because this limit would be too strict. The new code involves the material randomness factor and also a part of the behavior factor into this equation, allowing more deformations. There are other changes, but for instance, the material randomness factor, which was considered always as 1.25 in the current code, was revised to be different for the different string grades. And there are others here, but I don't want to spend more time, so I will stay in time. I will skip this part. As a result, having known these changes, we wanted to implement them in design and performance assessment. But at the time of the development, and still, because the code still is under revision, there are no commercially available programs to do these things, the design, and so on. So, an in-house tool was developed where Excel with Visual Basic for Applications VBA was used as an input generator for frames. OpenSys was used for the analysis, and Python code was developed to do design and visualization. There was okay. So the design has this objective. The flowchart is this: inputs will be given, analysis will be made, design checks will be made, and iteratively this was repeated with the objective of arriving at a frame with reduced mass. So the inputs are simple, given like this in Excel, here defining the geometry, here defining the load. From this, the program would generate the nodes, the elements, the connection stiffness, and so on, using the equal joints, the joints given by equal joints project. Here, analysis types are defined, and here, if needed, the individual member sections could be changed after generating. With this, a parametric study was carried out, where about 96 frames were studied, with regular and irregular spans between the frames, between base and the base, considering 3, 6, and 9-story frames, all at the same location, with peak ground acceleration of 0.35 g, and on soil type P, considering the current and the revised FT classes, using 2 material grades, and considering 2 approaches for the joint model. These are the results of the frame design. As you can see, it's visualized here. The loads and frame elements are visualized as such. And here, a color-coded design output is always shown, where yellow would mean approaching utilization factor about 0.8 or 0.9, and red would mean that the member has failed. And checks are made at the joint level if the capacity design criteria is fulfilled or not, where required. The results show that with the revised code, the value of theta was reduced on average by 55%, which allowed for lighter frames to be solutions, permitted solutions as for designers with the revised code. As you can see here, the value of the overstrains, the system overstrains, which is the element that was, let's say, more resistant or with the less utilization ratio, you see they're lower than the medians, and the means are lower than those given by the current code. For the materials, you see also the same thing. This is just to show the differences between the different typologies of the buildings and the number of stories, but here you don't see much of a difference. The results show that the frames designed to the revised code has reduced mass, as you can see. The red one is the revised code, and the blue one is the current code. So most the designs by the current code were governed by stability requirement, while those by the revised code where the stability requirement was not governed. However, the damage limitation requirement and some member resistance were governing the design. A frame mass reduction of up to 15% was seen in using the revised code. However, despite the larger Q factors that we use for ductility class 3 in the new revised code and ductility class H in the current code, it was seen that the ductility class 2 and ductility class medium frames were found to be lighter. So this was a concern, because the designers would assume in using bigger behavior factors for class higher class 3, they would assume that they would have a lighter solution in that sense, but that was not the case. The performance of these frames were assessed using nonlinear analysis, using trilinear model to model the web panel and shear, the web panel's behavior, and the interface between the beam and the column was modeled using the AMP model. So, and nonlinear static and dynamic analysis were carried out. For this were the seismic signals that were used to do the incremental dynamic analysis, whose mean is within a reasonable range to the, let's say, to the target spectrum. This shows that these model by these IMK models were calibrated using the test results from joints. The results of the pushover analysis are this. You see the base shear against the top displacement here. Save time, I'll skip faster because I'm left with short time. And the behavior factors were estimated from these results. As you can see here, considering the simplified model, you get bigger, larger behavior factors than when you consider the refined model. Frames designed to the revised code had smaller lateral stiffness, as you can see. So the broken line is the current code and the solid lines are the revised code. However, it was noted that the overstrength component has a significant role. And the factor that was given by the revised code, which accounts for every other source of overstrength to be equal to 1.5, was considered risky, at least in the assessment phase, because all the values were higher than that in our computations. If you see here, the behavior factor for redundancy, the behavior factor for ductility are there, and here is the behavior factor for overstrength. If you were to use these two only, or multiply them by a constant as is suggested by the current revised code, you would be implying, for instance, in this case, that the frames designed for using S235 material would have higher behavior factors than those designed for S355. However, when inputting exactly the values of the overstrength behavior factors calculated for each, the difference between these two narrows. The same can be said about the ductility classes. When you're using constant value here to multiply it, you would have more or less the same value, a significant difference between these two. On the other case, when you're applying raw value, the overstrength behavior factor, you'd see the difference between ductility class medium and high, ductility class 2 and 3. As you can see here. So the ones that are used in design are these, 6.5 and 4 here. Using this value or multiplying it by a constant would give you behavior factors that are equal for all cases, but when you're considering a particular behavior factor for each case, you can see clearly the difference in the behavior factor for the elements. The IDA gave reasonable results for all, so I will delve into this. I have discussed the results in detail, so I will not summarize here. So now let's go to the second part, which involves the literature review in selecting now, going from 2D to 3D, to see what is available in the literature. So these were part of the searched keywords, and the gaps found were that most studies studied minor access connections that are detached from the web or indirectly connected to the web using cover plates or bracket type connection, as you can see here. But some other studies were using connections that were directly connected to the web, and they found them to be practical or applicable. However, these studies were made only either in monitoring situation or where there was no interaction coming from the major access direction. So this was the gap. After seeing this, the research question became this: so where are we now? How accurately can we formulate, can we estimate the behavior of the column web under out-of-plane loading? To what extent can we use these types of connections in seismic regions, in low seismicity, medium seismicity, or high seismic regions or not? And what innovative solutions can be proposed to avoid plastification in the web, or at least hinder it? With this, we went into pre-test numerical simulations, where tests, about 45 models were developed to check the behavior of the column web under out-of-plane loading with 1 volt row and 2 volt rows, and also considering a thin plate connection or welded connection here for tubular sections. The results for the component characterization showed that the strengths that were estimated using the different yield line patterns, as you can see here, these are from numerical models, these are from the yield line models, were okay and sufficiently accurate, for instance, for Gomsh's model, but they have their limitations as they disregard the membrane resistance. And some other formulations were just empirical, with no physical significance. This is a comparison of the numerical model with the analytical formulations that were given there. And this shows you how material and nonlinear analysis and geometrically material and nonlinear analysis are different in this case, where the membrane effect at full, let's say, plastification could account for up to 20% of the full yield group. It was the same for the stiffness prediction. So, some of the proposals have limited application and were giving inconsistent results. For instance, here it's working fine, for instance, the Nevsch model. However, in this, the Nevsch model was not working fine. They have their own limitations. Knowing this, we went into designing an experimental campaign. So, the experimental campaign one, the test setup is shown here, where we wanted to study the component, which is a column web loaded out of plane. These are the specimens. Most of the action was on the back side of this image, so lots of you did not know what was happening from the windows or from the lab. So we were pulling this specimen this way out of plane using these connectors that were designed such that they could be used repeatedly with different bolt hole patterns. Sorry. 5 specimens of different lengths, web slenderness, and different bolt arrangements were tested, and digital image correlation was used to track how the web behaved as the loadings was applied. This is the instrumentation used. The location of the strain gauges and LVDTs were decided using the results of the pre-test numerical analysis. The material properties were tested and numerically simulated, and the inputs for the finite element models used the actual material models that goes from plastification until fracture. You can see here that we went into fracture model. Scanning was done to find the initial geometric imperfections. As the members were short, it was not a member type for imperfection that was governing mostly. It was the geometric imperfections there along the cross-sectional imperfections. And these are the results. What you see here is the images from digital image correlation at the final stages of the tests. And this here is the force displacement diagrams for the components. Numerical models were devised, were developed, in such a way. I will not go into details to the to the details of the modeling, but I will show you here the results of the numerical models, which are in red, and the results of the tests, which are in black, for the two tests, because these results are not published yet. I will not be presenting the rest of the results. But you can see that there is good agreement between these results. In addition to the force displacement curve, a cut was made, as I showed you earlier on here, along this line, and along this line from digital image correlation results, and compared against the results of the finite element analysis, and you can see that there is an excellent match between these two. You will see here how the stresses are concentrated and how where yielding was happening, where we have one ball throwing, where we have two balls, for instance. And then campaign 2 now involves not just the component under out-of-plane tension, but also under lateral combination, because a part of this disease involves understanding the interaction between several forces at the web panel zone. So, same specimen, rotated and kept here, but the difference is that now we have axial lateral compression coming from the other side, on top of the web panel being in tension. So you see, load was applied laterally and then maintained constant while the load was gradually increased out of plane from the web. And these are the results from digital image correlation again. This is the displacement out of plane, and this is the displacement due to the vertical load in the vertical direction. These are the force displacement plots, and again, there is a good match in the results between finite element model and that of the results obtained from the test. The finite element model modeled the top plate and the bottom plate that were used as bearing plates to apply the loads, and the deformed shapes, as you see, are matching. And in fact, the displacement here, about 3.2 centimeters that was measured in the test, you can see that here it was giving about 35 millimeters, and there is good accuracy level in the numerical models. Then right now we're in campaign 3, where we are studying now joints, not components of this type, as you see here, where we're applying load from the onto a beam and studying the behavior of the column web panel. And then a second setup will involve the same thing, but now with an additional beam connected to the column in the major axis direction as well. As you see here, so minor axis, and another beam connected in the major axis direction as well. And see, put one under monotonic load, constant, and the other cyclic and reversed in both directions. Considering the laboratory equipment that we have here, the initial plan was something different to apply by directional cyclic loading, but we have found that this would be a faster way to do it. I would like to take this opportunity to thank my supervisors and the visiting researcher that's with us, Jorge here, who accompanied parts of the tests. And honestly, the lab personnel here, without whose help this work would have not reached this far, because they helped a lot with the experimental part. And I thank you all for your attention. I finish it. Obrigado.
Thank you very much, Melaku. And now we'll pass to the questions. And the first one will be Josh.
Thank you for your presentation. It was a very complex one. I just have a few questions. If you don't mind, go to slide 6.
Slide 6.
Regarding the joint behavior, my question was what was the difference between all the joints you considered in your study, and when the one or the others can be applied?
So you're talking about these models?
Yes.
Okay. in my this design tool, there was the option to develop to model any of these joint types. You may not see it here, but this is a joint model. Here it was used for design, a simple one. But any of these could be modeled with the tool. The thing is, as we found this model to be the most detailed, closer to the reality, in assessments, the model used was this. And in design, I used the simplified model, plus these models. But it was indicated in another paper that we have published that using this is a little trickier because we are putting more springs at the same location, and it would be prone to numerical instability a lot of times. This one was found to be giving good results. The Craving. And also, since you asked where this could be applied. For instance, in the equal joints project, the behavior of the joints could be different. You could have a balanced weight panel, you could have a weak weight panel, you could have a strong weight panel. Where you have a strong weight panel, this model is fine, using rigid elements to represent the weight panel. But when you have weak and balanced weight panels, using the Craving model would be the most appropriate.
Regarding the slide 8, regarding the original revision code, I'm not familiar with the revision code, so sorry if that's not a question. It's not that it was too simple. But what's the major difference between the codes regarding the coefficients? Because I can see now the coefficients change a little. So what is expected for the building? What conditions for small buildings or big buildings will related to the coefficient that we will use?
Which coefficients?
The behavior, because now
the behavior factors.
Because from what I saw, the behavior factor now it's divided in different coefficients.
Okay, so previously, were these two behavior factors defined. So a value of 4 for rectangular class median and a value of 6.5. This is alpha u by alpha 1 was given to be 1.3 for non-resting frames, so a value of 6.5 for rectangular class high. In this case, particularly for rectangular class 2, it was relaxed a little more than rectangular class median. As you can see here, we are given a smaller behavior factor here, which means the structure will take more load. But the actions, the design actions that you calculate for each member are not as they were in the current code, because here you would amplify the shear, the axial force, and the bending moments with this factor, but in the new code, in the revised code, you would only amplify the axial forces. And in the end, you with this and also having this change in industrial drift coefficient, ratio coefficient, you would attain lighter solutions. So comparing to the current code, the solutions that you arrive at would be lighter. So less mass of steel would be required to achieve the same.
Okay. So regarding that answer, the slide 17, also regarding the coefficient behavior.
17.
Yes. So you also presented, I think it was after, some results from the comparison between different grades and different coefficients.
Yes.
So there's some building that was under the design regarding the original and the new error codes.
Under design?
Here regarding the new coefficients. Probably show the next slide.
Here?
You see, you show that some coefficients for 2, 3, 5 are better. Regarding the other factors, it was provided was the
yes.
weight. regarding if that coefficients have a big influence on that.
Yes, okay, I can explain it. Look, the new code, as I said, gave the total behavior factor as a product of these individual behavior factors that represent activity, redundancy, and all other sources. All other sources within itself holds the behavior factor for overstrains at least. And they gave the behavior factor for overstrains and all other sources as a constant, which was a value of 1.5. So, but as you see here, the behavior factor for the redundancy part, which was calculated after the fluid performance assessment, you'd see that S235 not so high, but closer, but still higher than that of the S355. Likewise, for the activity, you'd see that S235 would have higher behavior factor for activity than that of S355. If we were to take this and multiply it by the constant behavior factor for overstrains that is provided by the code in assessment, you would get a value for S235 which is higher than that of S355, which in reality is not the case, because when you consider the behavior factor for overstrains actually calculated from the frames, the difference between these two narrows to, I don't know, 10% or I don't remember the exact number, but you can read it in my paper, but it narrows down. It's not as big as this you can see here from this plot. So the conclusion from that work was that the behavior factor for overstrains has a significant impact, so should be considered, at least in the performance assessment level, not as a unique value for all, not to a constant value, 1.5, 1 for all.
Okay, thank you. Regarding the slide 59, your experiment. My question is regarding the tests used. How was the tests, the profiles used? So, what was the idea to use these profiles and not others, or why only use these case studies and not in a bigger scale to check for infections, or check for to basically to do a statistical approach?
Okay. It's a good question. Like everything in life, we're restrained by resources. I could not test all the sections that are available. These sections were sections that were available here at the lab, and we made a choice in varying them in terms of, because we're studying the column web, by varying the web slenderness ratio mainly. And then, from within that, we wanted to make the most out of it by finding representative sections, which here is an HEA 400, here is an HEB 400, you have an HEB 600 here, you have a plate, we have a plate girder here, which actually is at times high strength, fully, at times hybrid, with normal conventional steel in the web and high strength steel in the core, and also tubular sections. So we try to vary it as much as possible to obtain the most possible outcome from the materials that we have. That could be extended through numerical analysis after calibrating the results of these results. The results of these tests.
Okay, just a final question. I think it's the simplest one.
Okay.
Regarding the code you made for this project, what's your final goal for the project? To be open source, to a program that can be buy for a company?
Honestly speaking, I won't deem it that complicated to be, let's say, solved. It was something that I developed in 2019 and 20, while there were no visualization tools public for ISISE and so on. It is a valuable tool, and at the end of my PhD, I hope to share it here with the people here. It's not only that, but also the codes that I use for to develop models in Abacus, for instance, to do the coupon models, to do my models here, which are scripted in Python. I would need to first complete my PhD and then share them. In fact, these design and analysis tools, visualization tools that I made for 2D are now being improved for 3D, and they still have a few things to make better, which afterwards could be accessible for anyone. And the code for instance, at least material calibration, I know lots of you here do this in a repeated task. I think it would be good after having full confidence in the model that I have developed to share it so that other people will not waste time the same way I did, which took some time in coming days. But that's when you have this attitude of sharing, reciprocation.
Okay, thank you very much. It was a very good work. I don't have any more questions.
Thank you.
More questions?
Okay.
Maybe I could make a question. First of all, Melaku, thank you for the effort of making this presentation. From the experience you have going through the results of the tested joint, it seems through the equal joint campaign. I would like to know, have you came across a joint where, let's say, the linear stage is not so obvious, and the limit of linearity becomes so obvious? And in that case, how did you calculate the elastic stiffness? Do you have any recommendations?
Okay. In fact, when we joined Sarah there in 2018, I believe, 2018, the project was in its valorization stage. So the parts of the tests I was not involved in. So then in 2013, 14, I did many. So I've seen some of the curves that they produced afterwards. But in these types of joints, it is rather clear that you see the elastic phase clearly. But your second question, to find that point where plastification has started, it usually is not. In this case, in my models, I would be able to track it, at least not from the test. From the test, you find a curve. So what could be done? There are two ways of doing it. I would calculate always the gradient of curves, find the slope, find the second derivative of curves always, to find locations where change in direction is observed. That gives you an idea of where these changes are. And from the numerical point of view, I would always track the plastic strains models, and where there's plastic, when the plastic strain starts to build, that would be the stage or step where plastification is assumed to start.
Just to add maybe to the question. So let's imagine you have a designer who does not have the time or maybe the available tools to now recreate the joint. He just has in the literature a curve. He wants to apply it to a global model. What would be your suggestion? How to calculate? Is it a bilinear curve? That would be a suggestion. Is it?
I think it depends on what you want to take out of. Like I showed in the first two slides, you could model this joint behavior to different degrees of accuracy using different models. So if you want to be spot on, you need to model it as a nonlinear. Can you put the nonlinear behavior into the software tools that you use? But in many cases, for instance, the material properties that I have here, there are recommendations in the literature, for instance, that were developed by Leroy Gardner, for instance, to model material behavior. I, in my case, modeled the whole thing nonlinear, but there are simplifications as quadrilinear model that will give you reasonable accuracy. So it depends on what you want to extract. So simplified version could also do results, which it did in some cases. But when you want a detailed, for instance, in mine where I wanted to model the material until fracture, where fracture happened, I needed to go all the way. Depends on what outcome you expect of it. Experiments, frameworks. I really fancy with
You did in a way. Okay, we can elaborate on it later.
Sure, thank you.
Any other question?
Yeah.
Ladies first.
Now it occurred to me. Thank you for your presentation. As you mentioned before, usually in dual systems or we have moment-resistant frames, the frame that is the weak one, we call it, is usually taken by shear walls, or we use another system like bridge. So you're studying this combination of the dual joints. What do you think after you see the results of the joints, of course, more exploration about the effect on designers to take into consideration the contribution of this weak side, weak connection?
I think it's an area that we can explore still. Thing is, right now, simple pinned connections are assumed there, and in your model you put just the pins, moment releases there, and then you just rely on either the braces or the shear wall. As I mentioned earlier on, there is this, for instance, dual intercalary breast frames, for instance, these dual systems where you employ both the breast system and the moment resisting frame at the same time. By applying moment resisting semi-rigid connections in this direction, I think you could lower the load patterns, in this case, which is 25% taken by the moment resisting frame, and reduce use sections for the concentrate for the braces, and also the application could be even more other than just seismic conditions. In static gravity case also, instead of just assuming them to be pinned, you could take advantage of the moments and be able to save all materials. I think it's yet to be explored. It would be some recommendation that we would make after testing the joints, but I think they are closing to be applied. And there are works that recommend them actually.
Thank you, Melaku, for your great presentation and for work that you have done in your country. You touched that part that you did the simulation on the OpenSys, the panel. You used the Cloud.
Yes.
And I exactly the same. My question has different two sides. One of them about that part that when you introduce material behavior for the springs. Did you consider any degradation in strength, stiffness, things? This side and another side of my question is the times are also they are related to each other to the factor R or Q behavior factor. You know the behavior factor it has, as you said, 3 different parameters. And did you consider those in same level, the degradation, because you are talking about seismic and degradation that definitely in the annual zones or the plastic heat, it has important effects. How do you consider in the software frequencies and the other?
Good questions. First, about the implementation of the Krav model in my analysis. So I can explain. Yes, here. So for the panel zone, this trilinear curve was used without any degradation. However, the interface between the beam and the connection and the joint was modeled using the IMK deterioration model, which includes deterioration, as you can see here, stiffness and strength. So they were calibrated based on test results that were obtained from the project and input using using the modified IMK. This is one. Second one about this, you're asking me if at what point did I use them? They were taken at the same point. Yes. You have to define, I didn't plot the curves, the curve here, but you have to define a point where you consider the ultimate limit state has been reached. And the ultimate limit state was considered to have been reached, when the interstory drift exceeded 4%. So for all of them, the ultimate state was considered to be a point where the interstory drift exceeded 4%. So they don't lie at the same point because the trending is different, but a constant value parameter was used to determine those values, because here it is this factor, delta U over delta Y, that will be different. Because this, the base shear at the idealized yielding point will change. It's different between cases, but it will not be affected by the ultimate point. But here, the ductility behavior component of the behavior factor, which is affected by the displacement at the ultimate limit state point, that you consider, is related to the point that you raised. And yes, a constant value of 4% of interstory was used. This is the debate. There, for instance, in the American code, they would go SC, for instance. They would go all the way until the end, until a 20% drop in resistance is reached. So, but that parameter, it has to be fixed. And in my case, it was fixed at 4% interstory.
Questions? Okay. When you start this work, I know that like some time. You are now here.
Yes.
Yeah, for sure. So probably my question is a question that normally the students will have. I will help you with this one. This is a common question. It's about because you start time. It's about if you start your work now. What do you think changed with the process?
Good question.
I'm helping.
Yeah, I understand. It's with my experience for education. I think I've changed a couple. Honestly speaking, I could even start from the point of selecting the area. So, finding for instance, a project, an active project that was working in that area. Another point. I started this PhD as a student when I arrived here, but I was working in another project. So that would be a difference that I would take, a different route that I would take at that point. And since starting working directly on my PhD in 2019, I would have devised, let's say, a better way to do the experiments. And COVID was there also, so right now I'm doing experiments in my final year. If I would change things, I would have had how to change it. I would do the experiments in 2021. In fact, that was when I started doing it. Applying for it, but as you know, now resources are limited, you have share space, some materials didn't arrive, and so on. So that I will change and try to limit the amount of time that I take. And maybe perhaps now a little the scope so that things could run.
Thank you very much for your presentation.
and thank you very much for your answers.